Hello friends, welcome to this new lecture on amortized analysis. In this lecture, we are going to cover the first type of amortized analysis, that is aggregate analysis. So let's get started. Now, what is first? Let's understand what is an amortized analysis. So, in an amortized analysis, the time required to perform a sequence of data structure operations is averaged over all the operations performed. Now let's understand like how it is applicable. So amortized analysis can be used to show that the average cost of operation is small if one averages over a sequence of operations, even though a single operation within the sequence might be expensive. So what does it mean? This means that can be if you look at this particular diagram, suppose these are our instructions or these are the operations in our algorithm. Now a particular part of that algorithm suppose is slow because it is taking more computational time, or it is very like intrinsic. Suppose we are doing some kind of a matrix multiplication over here where we have nested loops. Okay, suppose we have three nested loops, so it might take a lot of time for computation of this particular part, wherein rest of the parts are very simple. Suppose they are just having big of one complexity because they are just constant time operations possibly. Okay, if, still just because of this part the entire algorithm is labeled to have a higher complexity. So can we do something to lower the complexity of that algorithm? Can we average out the complexity of the most expensive part over all the operations? So that is what is amortized analysis. So we have various operations here, right? So the Tn, okay, that is the complexity of time, okay, for the entire algorithm is divided by the number of operations. So this is how we average out the complexity over the number of operations present. So we'll proceed and understand the difference between first amortized analysis and average case analysis. Now, amortized analysis differs a lot from average case analysis. Okay, the basic difference is that amortized analysis doesn't use probability. Okay, so in any method that you're going to learn, you are not going to come across any kind of probability usage. Wherein in average case analysis, it uses probability. Now, amortized analysis guarantees average performance of each operation in the worst case. So obviously the worst case analysis, whatever it is there, okay, but for single operation now we'll be having an average case, an average performance, not the worst one. So now there are three techniques. The first one is the aggregate method, the second one is the accounting method, and third one is the potential method. And there are three examples that we can take to explain each of this particular method. In this particular video lecture, we'll be looking at the aggregate analysis. So let's get started. Now, so what is aggregate analysis? In aggregate analysis, for all n, a sequence of n operation takes worst time t of n in total. In the worst case, the average cost or amortized cost per operation. That means here we take the total cost, that is T of n, right, and divided by the number of operations. So finally, every single operation will be getting some particular average cost. Okay, so that is aggregate analysis. Now, so let's understand with the help of an example. So the first example is the dynamic tables. Now, so what happens in dynamic tables? So obviously in this also some operations might be expensive and some operations might be just average. Okay, some will be just having a constant time complexity. Okay, so we need to average out, right? So first let's figure out like how is the working of dynamic tables and what are the most expensive operations in this. Okay, now, so let us consider an example of a simple hash table insertion. So now first understand what is a hash table. So everyone knows that suppose I'm talking about a library and I want to put the books inside the shelves. So suppose I have just five shelves and I have the various book numbers. Okay, book with some numbers. Now I can just use a simple hashing mechanism of using mod operation. So if I use the mod operation, what I could do is like suppose I take book number 22 and I mod it by 5 because we have only 5 shelves. So I get the value 2. As soon as I get the value 2, I place this particular book number 22 into shelf number 2. Okay, so later also if I want to search any particular, like if I say I have book number 27, so I'll know where to search it because obviously mod of 27 by 5 will give me value 2, and again this book will go into shelf number 2. So that is how it becomes easy, right? So that is hash table insertions. Now, how do we decide the size of the hash table? The thing is that if I'm having a library, obviously I'll decide on the basis of how much space I have for the library and how much shelf I can build in it. Okay. So similarly is your case in your computer, like how much memory you want to allocate to this particular data structure. Okay. If you suppose think about of a big array. Okay. So obviously this big array is going to have a lot of space, and so the space complexity goes first, but yes, the time complexity reduces because searching in a table, okay, this element will get its own location, a particular element possibly, and it doesn't have to share the location with some other elements which is having the same mod value. Okay, so in that case possibly we might have the search time which is very fast, but the space required will be also very high, which is a bad thing. So it's a trade-off between both space and time. Okay, you reduce space, time increasing, you increase space, time decreases. Now, so how to work about it? Okay, so we have a solution for this, and that is the dynamic table. So now what is a dynamic table? In dynamic table, the first step is like we need to understand when the table goes full. So as soon as the table goes full, what do? I allocate a new memory location of double the size of that old table. Then I copy the contents of the old table to the new table, right? And I then free the old table. Now in the new table, obviously I'll be having more free content because it's the double the size of the old table. So whatever new data comes, I can specifically just allocate it into the new table. Okay, and I can keep on going till the again the table is full until unless I go for I do have to double the size of the table. Okay, so that is how it works. Now so this is an example of dynamic table. So you can see the item 1 it has come, okay, and item 1 as it goes, okay, there and there itself it realizes that the table is full. As the table is full, what it does, it doubles the size of the table, and the second element is inserted. When we insert the second element, again we realize, oh, the table is full again, so I have to double the size of the table. Whenever the size of the table is doubled, you need to understand that the old table values, this is 1 and 2, has to be brought on into the new table, right? And then a third element, new element comes in. Okay, similarly a fourth element comes in. When again 1 2 3 4 are done, okay, we realize that the table is full. We double the size of the table. We copy the first four values again back into the new table, and then we insert the fifth one. So there's no doubling charges or no doubling operation for 5 6 and 7 and even 8. Only when we try to put up 9, we have to again double the table to the size of 16, right? Now, so you need to understand that if we use simple analysis, the worst case operation of an insertion, what would it be? It's like I have to check in every shelf, okay, where I have to put the book possibly, okay, I have to go through all the shelves, right? So that if there is a like n shelves, I can say that the complexity is big of n, okay? So but if we are talking about just one insertion whose complexity could go up to big of n, then for n insertions, the complexity could go up to big of n square, right? So obviously that is an upper bound, okay, but do you think it's a tight upper bound? It's not. Okay, so you need to understand that the complexity, we know what the worst case complexity might be, but that is not a tighter bound. Okay, it's something which is vague, it is something which is very high. Okay, so now in this case we need to find out the average analysis, that is the theta of n instead of big of n. Now, so let's try solving this by aggregate analysis. What do we do in aggregate analysis? It's the T of n divided by n. So it's the cost of n operations divided by n. Now, what is the cost of n operations? If you see, the cost of n operations in this case is the cost of normal operation, that is of insertion, and cost of expensive operation, that is of the doubling and copying, right? So let's understand how it works. Now look at this table. In this table, when you see, okay, and I insert item 1, okay, at that time I need not do any doubling. So obviously the total cost is 1 because the cost of operation is only 1. And if you see the entire column, the cost of insertion is just 1, right? Now if when I go for insertion of the second element, I see that I have the total cost is 2, wherein the cost of operation is 1 and the cost of doubling, okay, that is also 1 because we have to copy and double and copy one element, right? That's why. So the total cost is 2. For 3, again we have to double, right? So the table size goes from 2 to 4, and I have to copy the first two elements as well. So the copying on doubling of the elements, this is 2, and the third element which was inserted, that is 1. So this is 1 plus 2, which is 3. For the fourth element, obviously there's free space available, so I can just insert. So you can see the total cost is 1 because there's no doubling cost. There's only insertion cost. Similarly, when I try to put the fifth element, I have to double the array. When I have to double the array, I have to copy the first 4. So you can see doubling and copying reach to 4, and the insertion of the fifth element is just 1, so the total cost is 5. Okay, similarly, you can go up till 8. When you put up the ninth element, again the same thing happens. Yeah. So we need to figure out in this case that how much is the cost of the normal operations and how much is the cost of doubling. So do you see the cost of doubling and copying in every single step? No, it is happening very less than the normal operations, right? So can we figure out a relation that how many times that the doubling operation is happening, right? So we can do that. So let's check out how we could do it. Okay, so we can see that if I'm putting up the eighth element. Okay, so before eighth element, how many times I might have done it, right? So can you say, can we say that we might have done the doubling operation log n times? So if this is the eighth operation, eighth element, okay, so log of n is 3. You can see 3 times we have done this before eighth, right? As we go for the ninth operation, right? So in the ninth operation, okay, while doing the ninth operation, we do the doubling, okay, but even before 9, we see that we have done it just 3 times, right? So we can say that it is log of n minus 1, okay, the amount of times we do the expensive operations. So let's go to that part. Okay, so if I say that I have to check the cost of n insertions, I'll be just adding this total cost, right? I'll be adding this entire thing. Now, so when I'm adding this entire thing, okay, it is actually what? It is the cost of operation plus the cost of doubling. Now, cost of doubling, okay, how many times do we do it? Okay, you need to figure out that out. Okay, so you can see that it's a geometric progression that we are using. Okay, it's a summation, but it is a summation of 2 raised to something. Okay, so in this case, you know that this thing might turn out to be 2n, right? And so it will be 2n plus n, which is equal to 3n. So you can see the cost of an operation is less than equal to 3n, right? So finally, we can say that is the average case analysis. Oh, sorry, average case. Okay, for because we had seen that the worst case might go up to n square, and you can say now it is just theta of n. So now the using the aggregate analysis, we can say the average cost of each dynamic table operation. So now we are talking about each operation, not the entire operations. Okay, set of operations. So for each operation, you can say that it is theta n divided by n. So for each operation, you can see that it is just theta of 1, which is a constant time complexity that is coming out using the aggregate method. Okay, so it's the aggregate analysis and is the aggregate analysis of amortized analysis. So finally, we have come to a conclusion that this gives us a way better result when we average out the complexity overall all the operations. So now in the next example, we are going to look at the stack operation, and we'll be understanding the similar using the aggregate method how to solve the same. Okay. Now let's look at the example of stack. So in this example, we are going to understand the amortized analysis and the technique that is aggregate analysis with the help of stack example. Now in stack, we know that there are two main operations, that is the push operation and there is a pop operation. We also know that both the push operation and the pop operation, they have a constant time complexity of big of 1. So let's understand how they have a constant time complexity. So let's understand what happens in a push operation. We know that in the push operation, we just check whether the stack is full. So we check whether the top of the stack is equal to the size of the stack. Okay, if it is equal to the size of the stack, that means that it's already full. If it is less than the size of the stack, then we can push an element into the stack, and then we can increment the top counter. Similarly, if we want to check with the pop operation, what do? We again use a if statement to check whether the top is pointing to -1. That is, it's having no elements inside the array. So if it's, or you can say linked list. So that's how we figure out whether the element is there or not. Okay, so all this operation, we just have if statement, or we have an assignment statement, or we have an increment statement or a decrement statement. So such statements which are there, it just means that these are having or what constant time complexity. So constant time complexity, that it actually leads to and understanding that push and pop elements are having a complexity of big of 1. But if we are doing this operation for n elements or n operations are we performing, so it is like n into big of 1, which will result into big of n. So it only happens if you are dealing with n inputs or n pop operations, right? Now, so let's understand that what would be the case if we use one more function called as multipop. So this is a made up function. Now we know that you can clearly see that the running time for the push operation is big of 1, for the pop is big of 1. So what is multipop? Multipop is like we want to pop out k elements. Now this k element, okay, k is a number, and suppose n is the size of the stack. Okay, so we have to check. Okay, like in this case, we can say that the s is the stack, right? So we have to check that is k less than the stack size, right? So if it is k is less than the stack size, that only k elements will be popped up, right? So when k is popped off, the complexity would be what? K elements. But if suppose k is greater than the size of the stack, so obviously I can't remove elements like if only have n elements inside the stack, I can't remove more than n elements. So someone asked me to pop up 100 elements, but I have only 60 elements inside the stack. I can't take out more than 60. That means I have to choose the minimum. So the minimum would be what? So in this case of multipop, it is the complexity is minimum of either k or s. That is the number of elements inside the stack. Okay. So if the k is less than the number of elements, so complexity is k. If number of elements is less than k, then the complexity is number of elements. That's how it works. Now, so let's understand the stack example with the help of this multipop operation. Now, we know that like now a new operation is added to the stack, that is multipop. Now, multipop will either pop the top k elements in the stack, or if it runs out of elements before that, it will pop all of the elements in the stack and stop. So this is the working. Now the pseudocode for multipop, you can clearly see we have a while condition which states that if the stack is not empty and k is also greater than 0, right? So only then you pop off one elements till we reach k elements, right? And we keep on decrementing the k value, right? And that's how we pop. So now looking at the pseudocode, it is easy to see that this is not a constant time operation like push and pop. It is just a big of one, but this value kind of depends on the how many values we are trying to pop out. So multipop can run for most n times, right? Maximum it can run only for n times, because the k value is like saying a pop of 100 elements, but the size of the stack is just 60. So can you run more than that? So maximum times it could run is just 60, that is n sub. So where n is the size of the stack. So the worst case runtime for a multipop operation is big of n. Now, so this is worst case runtime for one multipop operation. Now, suppose you are thinking about n multipop operations. So the obviously in this case also the complexity might lead to what? N into big of n, which is big of n squared, right? Now, so however, that is not actually the case. Okay, you clearly know that it's not big of n square. So you need to figure out how. So for that, we need to actually see how multipop works. So multipop cannot function unless there is a push to the stack, because it would have nothing to pop off, right? So in fact, any sequence of n operations of multipop or pop and push can take at most big of n time, right? Because obviously if there are only if there are n push operations, then we can have n pop operations, right? And if you're talking about multi-pop, we can pop off all the n elements in just one operations itself also. Okay, or if the value of k is 1 in multi-pop, then we can do n multi-pop operations. But obviously if the k is 1, it can't exceed more than n, right? This operations that we are doing, it can't go above n. So finally, even if you are working with multi-pop, the complexity is not going to go more than big of n. So the only non-constant time operation in this stack, okay, multi-pop is what? Only the non-constant time operation can take big of n time if there has been like n push operations, only if there are n push operations, right? So in the very worst case, there are n constant time operations, that you can say push operations, and just one big multi-pop operation, that is big of n time. Okay. Now, for any value of n, any sequence of multi-pop, pop, and push takes big of n time. So using aggregate analysis, we know that it is t of n by n, that is, and finally we have come to a conclusion that t of n is equal to big of n, so big of n divided by n. Finally, we know that each operation, let it be pop, multi-pop, or push, it's going to take just big of 1, right? So it's a constant time algorithm for an operation, okay, for one operation. Okay, so this is the stack example. Hope you have understood this. Now we can proceed with the next example, that is the binary counter. Okay, now what happens in a binary counter? So let's see how binary counter works. So you can see these are the rows. Okay, so every time I call the increment operator function, it's going to work on this particular array. Okay, so please follow my pointer. This is an array. Okay, wherein the array first position is 0, then 1, then 2 and 3, and all the like values inside this arrays are 0. Now, so this is the first array that's been passed to the increment function. Now in this increment function, I see that if my I is pointing to 0 right now, if I is less than k, what is k? The value of k is 4 because the size of the array is 4. And if a of I equal to 1, so we can see the first element which is there, it is not equal to 1. That means my while loop is not going to run, and if it is doesn't run, I directly check whether I is less than k. Yes, 0 is less than 4, right? So in that case, what do? I do a of I equal to 1. So you can see just 0 is converted into 1, and you can see the output in the next array. So this is the output, okay, that comes after we pass all four zeros to this particular increment function. Similarly, when I push past this array, the second row as an array, to the increment function, what happens? So it's like I start again from I equal to 0 and I surely less than k, and if I encounter a of I equal to 1, what do? I convert it into 0, right? And then I increment the I operator. So you can clearly see as 1 was encountered, this 1 was converted into 0, and I got incremented to the next point thing, that is 0, right? Now I is pointing to the first position. Okay, I is pointing to the first position. Now I come over here, I again check 1 is less than k, that is k is 4, like 4 elements. So obviously in this case, a of I'll convert it to 1. So you can see as I is pointing to 1, I convert that particular a of I equal to 1. Are you getting it? Now going ahead, so similarly as this the third row is passed to the increment function, you can clearly see this while loop won't run because the first element is 0 itself, so this doesn't satisfy, and I directly convert that 0 into 1 because of this if statement. Similarly, when I pass the fourth row to the function increment, what happens? I see that it satisfies this, okay, and a of I is converted into 0. So you can see 1 is getting converted to 0. Right. Similarly, if I is incremented and again this particular 1 is converted into 0. Right. And now the while loop doesn't run because we have 0 over here. So it doesn't satisfy. But when as soon as it comes out, it converts that 0 into 1. So you can see now the array which was 0, 0, 1, 1 has been converted into 0, 1, 0, 0. Okay, so actually we are moving from right to left. So we should say that the array which was 1, 1, 0, 0 has been converted to 0, 0, 1, 0. Okay, so this is how the binary counter works. So now you can see that we have n sequences. So what are n sequences? Like we have 16 sequences, right? We have 16 sequences, and number of array used for that is a number of bits in the array to show this like 16 sequences are 4. So we can clearly relate that number of sequences is related to the number of bits in the array. How? So if n is equal to 16, okay, we can say that it is 2 raised to 4, which is 2 raised to k, right? Now, so that's how we can say that n equal to 2 raised to k, right? N is equal to 2 raised to k. If we see such kind of a thing when n equal to 2 raised to say k, we know that k is always equal to what? Log of n, right? So number of bits which is k is always equal to log of n operations, right? Now going ahead, let's see how can we understand the worst case complexity for binary counter. Now in the worst case situation, a single execution of increment takes big O of k time. That means that in the worst case situation, I might have a situation like the 16th row. Can you see in the 16th row, we have all four as ones, right? So as soon if I pass this particular array to the increment function, all these ones will get converted into zeros because of the while loop. So that means we can encounter four change, all the 4-bit change we can encounter over here. So that is big O of k, right? Now, this big O of k, where k is the size of the array, in which array A contains all ones. Thus, a sequence of n increment operations, right? N increment operations if we are doing. Okay, that means n sequences. So if the worst case could be big of k, then for n operations we can say that it is big of n into k. That is the worst case. But obviously that is not true. We don't change every bit, all the bits every single time, right? So let's understand how the bits changes. So you can see that how the flip happens. So you can see the a of 0. there's a continuous changes in the bit, right? The continuous flips you can see. As we go and see a of 1, we can a of 1, you can clearly see that it is n by 2 times. Okay, that means we can say that this flips happens. Okay, not n times, but a we can like in this case it was 16 times flips. Here it is 8 times. So 0 to 1 is 1, then here 1 to 0 second time, then 0 to 1 is third time, then 1 to 0 is fourth time, then 0 to 1 is fifth time, then 1 to 0 is sixth time. Okay, similarly how it goes, and you can say that it is changing with respect to n, that is we can say round about n by 2 times. Similarly, this is also like n by like 4 times. Right, here we can say it is flipping n by 4 times. And the last one I can say that it is just around flipping almost like n by 2 times. Right, so we can have a relation now between the bits, and we can say the number of times it flips. Okay, the position of the bit and the number of times it flips. So what kind of relation can we have in this case? So we can see that if a bit is flipping, if we are talking about an ith bit, how many times it's going to flip? Okay, it's going to flip n by 2 raised to I times, because this is n by 2 raised to 0, this is n by 2 raised to 2 for the second position. So if I'm talking about the ith position, it's going to flip n by 2 raised to I times. Right, now obviously n by 2 raised to I, if I'm talking about, then it's a similar case, right? Like in here, n equal to 2 raised to k, right? So we talk about k as log n. Right, so in here, obviously, if it is n by 2 raised to I, so that makes it like again n equal to instead of I where we had k, so we can say I equal to log of n, right? So that means I'll be iterating how many times? Log n times. So from 0 to log n times, okay, I'm saying that we are going to work out n by 2 raised to I. Now, this thing, you know that it is less than, okay, obviously it's going to be less than, okay, if I remove change log n to infinity, it's going to be less than, right? So it is n of 0 to infinity. And I've just taken n outside. So we are just talking about I over here. Now, if we see that this is what? This is a geometric progression, right? And if you're talking about a geometric progression, we can say that this can be converted into, okay, this particular sequence, that is 1 divided by 1 minus 1 by 2. Okay, when I do this, this gives me the value 2. So I multiply 2 by n and it comes to 2n. So I understand this particular entire complexity of this function is coming less than 2n. And what had we said before? That it was equivalent to n into k. So k was 4, right? So it was big of 4n. But we can clearly see it is still less than 2n. So my big of n is just less than 2n. And finally, you can see that it is big of n by n. So aggregate analysis gives me big of 1. So I hope you have understood. Thank you for attending the lecture. Happy learning. Enjoy algorithms. Thank you.